I welcome my viewers and students to this lesson on Group 1 Alkali Metals of the periodic table. I want you to subscribe, like, and comment and share this video. As we progress in this lesson, we will be studying the alkali metals, and I want my students to be able to identify the elements in Group 1 of the periodic table by the end of this class. They should be able to write their electronic configurations, describe the periodic trends of the Group 1 metals, explain the differences between an atom and an ion, and write the equations of the formation of their oxides, hydroxides, and their halides. The element and symbol of the Group 1 metals will have the elements as hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen has atomic number 1, lithium number 3, sodium 11, potassium 19, rubidium 37, cesium 55, and francium 87. Their electronic configuration always ends in the S of shell, with hydrogen ending in 1s1 shell, lithium 2s1, sodium 3s1, potassium 4s1, rubidium 5s1, cesium 6s1, and francium 7s1. It tells us that they have one electron, one valence electron always in their outermost shell. As students, it's important that we learn this electronic configuration. In this group, we have the uniqueness of hydrogen, because hydrogen forms covalent bonds, while other members of this group forms ionic bond. And the uniqueness of hydrogen will be discussed in subsequent class. Occurrence and extraction of Group 1 metals. Extraction, we know, is the process of separation of an element or compound from a mixture. The alkali metal cannot be extracted from their native or pure state. They cannot be found in their native or pure state in nature because they are extremely chemically reactive. They are strong reducing agents and cannot be extracted from their ores. Specifically, they react violently with water. As such, alkali metals are usually found as salts like sodium chloride, potassium carbonate, as nitrates, and as sulfates. We have said that they cannot be extracted from their ores as they are strong reducing agents. If we look at the equation between sodium and chlorine, for that equation to take place, sodium has to donate one of its outermost electrons to chlorine to form that sodium chloride salts. They are highly reactive, and because they are strong reductants, obtaining them in their pure form requires a considerable input of energy. Pure lithium and sodium, for example, are typically prepared by the electrolytic reduction of their molten chlorides, as shown in that equation, and then cesium is extracted from aqueous solution. Flame nature of alkali metals. When a flame test is performed, the metal ions in the sample must be atomized into the hot Bunsen burner flame. This is made easier if the sample is made into a metal chloride salt, because when it is converted to a metal chloride, it shows that more volatile metal salts are easily evaporated and the flame test is more visible. For lithium, it will be red. For sodium, it will show a yellow color. For potassium, it will show lilac. For cesium, it will show blue. And for rubidium, it will show red. The reactivity of the Group 1 metals. These are soft and stable metals, and they have low ionization energy and low melting points. They are highly reactive. As we move from down the group, we see an increasing reactivity. It increases on descending the group from lithium to francium. Then we have these atoms are larger because they have more shares, as shown in the diagram. We'll have their inner nucleus, and then we'll have for lithium, and then we'll have two shares there. And then we'll have for sodium the inner nucleus, and we'll have three shares, and it keeps on increasing. The number of shares keeps on increasing, becomes larger as we move down the group. The larger the atom, the farther the outer electron is from the nucleus. And the force of attraction between the nucleus and the electron is less than for smaller atoms, and the outer electron is lost more easily. Formation of ion. An alkali metal have one valence electron in its outermost shell, and they are able to donate this electron easily to obtain a noble gas configuration. When this electron is donated, the alkali metal charge will change to a positive one because they have become a positive ion, also called a cation. They lose their outermost electron when it forms a cation, and it makes their shell smaller. Their shell becomes smaller as they form the ion. Their metal ionic radius tend to be smaller than their atomic radius. The sodium atom has 3 shares, while the sodium ion has 2 shares. If the atomic radius is measured, which is the distance between the nucleus to the outermost electron, you find out that the distance of the nucleus of the sodium atom will be higher than that of the sodium ion. The sodium cation is smaller than the sodium atom because it had to lose an electron to form the ion. Sodium lost an electron share when it lost an electron. Atomic and ionic radius. The atomic radius is the distance between the nucleus and the electron in the outermost shell of the atom, while the ionic radius is the distance between the nucleus and the electron in the outermost shell of the nucleus of the ion. Looking at this diagram, we have the sodium atom, the sodium ion, the potassium atom, and the potassium ion. The sodium atom ppm is 190 ppm, while the sodium ion ppm is 116 ppm. Potassium atom has a ppm of 196 ppm and potassium ion 152 ppm. We have seen from the structures that the sodium atom is bigger than the sodium ion because for an ion to be formed, an electronic shell of the sodium atom will be completely lost. One electron was lost from the atom and it formed a sodium ion, meaning that sodium gave out its one electron. It applies to potassium atom also that gave out its one electron to form the potassium ion. So we can see that ionic radius, increases down the group. Also, atomic radius increases down the group. So atomic shell increases, atomic radius increases, density and ability to lose electrons to form positive ions increases down the group, and the melting and boiling point decreases down the group. It is easiest to withdraw an electron for cesium metal. Hence, the correct order of ionization potential of group is lithium greater than sodium, greater than potassium, and greater than cesium. Formation of their oxides. Alkali metals react with atmospheric oxygen and get tarnished for their shiny nature. They bond with oxygen to form oxides. but the nature of oxide formed is different. Oxygen has a different oxidation state in their oxide. The oxides of lithium are normal oxides. Sodium can form both normal oxide and peroxide, and the larger elements like potassium form what we call the superoxides. Like the equation with the lithium there, it has formed a normal oxide. That oxidation number is -2. When it reacts, in the case of sodium, to form the peroxide, the oxidation number is -1. The peroxide is Na2O2. And then for potassium, it will form the superoxide KO2 with an oxidation number for oxygen as -1/2. Since the alkali metals react with nitrogen, oxygen, and water in the air, they are always stored under kerosene. Hydrides. Lithium ion and the hydride are approximately of small size or of same size. The charge density is high between the two. Thus, the ionic bond so formed will be very strong, and hence more will be the lattice. Alkali metals react with hydrogen at higher temperatures to form metallic hydrides. Metallic hydride release the hydride. We have the equation there, 2M. M can be any of the alkali metals plus hydrogen to give us 2MH. From that metal hydride, it can also decompose again to get the metal and the hydride. So we'll give an example of lithium reacting with hydrogen to form the lithium hydride, and then sodium reacting with hydrogen to form the sodium hydrides. And these hydrides are strong reducing agents. Reducing nature increases down the group. They are ionic solids with high melting points. Their ionic character increases from lithium to cesium. As the size of the metal cation increases down the group, the lattice side energy of the hydride decreases down the group. The reactivity of the alkali metals towards hydrogen decreases down the group. Reaction of the hydroxides. Alkali metals react with water to form basic hydroxides and liberate hydrogen. The reaction of the metal is exothermic, and the enthalpy increases from lithium to cesium. Alkali metals float on the water during the reaction. The group 1 metals react with water to form hydroxide and hydrogen gas. Lithium solid react with water liquid to form lithium hydroxide and hydrogen gas will be liberated. Sodium solid react with water liquid to form sodium hydroxide and hydrogen gas will be liberated. Potassium solid react with water liquid to form potassium hydroxide and hydrogen gas will be liberated. All these reactions, the one for lithium is not deliquescent, but for the one for sodium and potassium, it shows deliquescent reactions. The aqueous solution are strongly alkaline, hence the name of this group called the alkali metals. Their name is derived from the fact that they are strongly alkaline. They form strongly alkaline aqueous solutions. They neutralize acid to form salt and water. Sodium hydroxide plus HCl react to sodium chloride and water. That will be what they will form. The oxides and water. Their oxides yield hydroxides when reacted with water. Lithium oxide react with water to form lithium hydroxide. Sodium peroxide react with water to form sodium hydroxide and hydrogen peroxide. And potassium oxide, which is a superoxide, will react with water to form potassium hydroxide, hydrogen peroxide, and oxygen. The alkali metal halides. All metal halides are white ionic crystalline solids. They contain the elements of the group 1 and group 7 of the periodic table. The higher the number, the more ionic the solid is. From the table shown, you can see that these metals react with the halogens. They can react with fluorine, with chlorine, with bromine, with iodine. And the ionicity increases down the group. For the fluorine, lithium fluoride 3.0 and then cesium 3.3. Chlorine, lithium chloride 2.0 and cesium chloride 2.3. It just increases down the group. It applies to the bromine and to the iodine. They are very reactive. When you put the group 1 and the group 7 element, just know that reaction will take place. We have come to the end of this lesson. We will have some studies questions here for us to attempt. 1. What is a reducing agent? 2. Why are group 1 metals called strong reducing agents? 3. List the species in order of increasing size: rubidium atom, rubidium ion, fluorine atom, fluorine ion. 4. What is an ionic radius? 5. What types of oxides do lithium, sodium, and potassium form? And 6. Why does ionic character increase down the group? Thank you, as we have come to the end of this lesson. I hope you enjoyed this lesson. Don't fail to subscribe, like, comment, and share. If you're a parent, share this lesson to your children. If you are a student, share it with your friends. It will help them in the class. Thank you and see you in the next lesson.